Hello, everyone. Today we're going to talk about the speed of sound in gases. What are we going to do? First, we're going to review the difference between extensive and intensive properties. We're going to talk about what is heat capacity. We're going to talk about the conservation of energy. We're going to talk about constant volume heat capacity. We're going to talk about the equal partition of energy theorem. Then we're going to review some calculus. We need this calculus to kind of move forward with relationship between CP and CV. We're going to discuss degrees of freedom, the Einstein's model. We're going to discuss the experiment, even though we're not going to do it this semester, and then of course, safety. All right, so what are extensive and intensive properties? An extensive property depends on the amount of substance you have. Some examples are mass, volume, weight. Extensive properties are additive. If you have mass 1 and mass 2, those two masses can add. Mass 1 and mass 2 is the sum of the total is the sum of those two masses. Density, however, is an intensive property. Let's say temperature, melting point, freezing point. These properties are not additive and do not depend on the amount of substance you have. Again, let's say we have a blob, some object, and it has some uniform density, and maybe we cut it in half. Well, the density isn't cut in half. The blob on the left has the same density as the blob on the right. Again, intensive properties are not additive. Okay, so what is heat capacity? Basically, let's say we have some blob of mass and we add some heat to it. The heat capacity is a measure of how much heat we can add to some blob relative to its temperature change. So let's say we have some mass and we add some heat to it. And if the temperature changes just a little bit, then it has a high heat capacity. But let's say we have a different mass and we add the same amount of heat to it. If we do that and the temperature changes a lot, then it has a low heat capacity, okay? Heat capacity is an extensive property. Basically, if we have blob 1 and blob 2, and they each have some heat capacity, well, then the total heat capacity is the sum of those two blobs. Specific heat capacity, however, is not additive. Specific heat capacity is an intensive property. Kind of like density, okay? This is the same with molar heat capacity, okay? The specific heat capacity is just basically heat capacity per unit mass, and molar heat capacity is heat capacity per unit mole, okay? So conservation of energy. Here we're only going to deal with PV work. We're not going to deal with, let's say, electromagnetic work. So we know that the change in energy of some system is equal to the heat added or lost by that system plus the work done on or by that system. Okay, but here I have something interesting. I have du equals dq minus PdV. Okay, so now sometimes students are wondering about this minus sign here. Why is there a minus sign there? We just said that change in energy is equal to the heat plus work, but we add this minus sign here. So let's think about this minus sign. So this is relative to the sample under discussion. Okay, so let's look at this here. Let's say we add some heat to the sample. We add some heat to it. So this is positive. Okay, that makes sense. But now let's consider this dV here. Let's say we do work on the system. So if we do work on the system, if we compress the system, then dV is negative. So then P dV, this whole thing with a negative will be positive. Negative times negative is a positive, okay? But let's say the system does work. If the system does work on the surrounding, it has to lose some energy, and so dV is going to be positive. The system is expanding against some external pressure. In that case, this is positive, so this is negative here. So that means the internal energy decreases, of course, when the system expands and does work on the surroundings. Okay? Okay. Okay, so the same thing we just said before. Okay, so we have change in internal energy is equal to the heat lost or gained by the system minus PdV. Now let's fix our volume, okay? So let's say dV is 0. So if dV is 0, then this whole term here is 0. So that just means we have du equals dq. So now only heat can enter or leave the system. The system can't change in the system can't change in volume. Okay, but let's look at this while changing the temperature. Okay, so let's say we divide by dt. Again, you can't actually divide by dt. You divide by delta t and let delta t go to 0. So we have du dt is equal to dq dt. But we saw just a few slides ago that dq dt is our heat capacity. And specifically, we're talking about heat capacity at constant volume. So CV, heat capacity at constant volume, is equal to du dt at constant volume. So let's just, that's important. So let's just go over that one more time. So again, we have this here. We have dV is 0. So this term here is gone, okay? So we just have du equals dq. So we have a constant volume system, okay? So if we look at this with respect to changing temperature, we have du dt equals dq dt, okay? But again, this thing here, that's just heat capacity. But again, I said we're under constant volume, so we have the heat capacity at constant volume is equal to du dt at constant volume. Okay, great. Equal partition of energy theorem. So this is a classical argument, okay? So basically this says that all the modes or all the degrees of freedom have the same energy associated with them, okay? This energy is INRT over 2, okay? Okay, so I is the number of degrees of freedom, N is moles, R is ideal gas constant, T is temperature, okay. So this is assuming that all the modes are populated. What does that language mean? That means that I can add energy to any available mode or degree of freedom. You may think, well, that's obvious. But as we'll see in a little bit, actually, there are some modes that at room temperature you can't add energy to, or at least there's a very low probability to add energy to them. Let me just give you a quick example. Nitrogen has a vibrational mode, I don't know, 2300 wave numbers or something like that. At room temperature, there's a low probability that this mode is populated. There's a low probability that you can add energy to that mode, okay? So that mode doesn't really contribute to the heat capacity of nitrogen, okay? We'll get back to nitrogen. Okay, so anyway, in the last slide, we saw that the heat capacity at constant volume is du dt. So if we differentiate this with respect to temperature, we just have INR over 2, okay? So we have CV equals INR over 2. I just want to stay here just for a minute. So sometimes you can write heat capacity, and I'll do this for the rest of this lecture, in dimensionless units. So if you have CV equals INR over 2, and you divide both sides by NR, you have CV over NR is just I over 2. That just makes the calculations easier. Working with dimensionless units is a lot more pleasant. Okay, we'll come back to that. But before that, I just want to quickly review calculus. We're just going to use this just a little bit. So let's say we have some function. F of xy is 7x plus 3y squared, okay? So let's differentiate this with respect to x. Well, this term right here is not a function of x. So when we try to differentiate this with respect to x, it's a 0. It goes away. But this 7x, if we differentiate it with respect to x, we get 7. So the derivative of this whole function here with respect to x is just 7. So if we look at the same function here and we differentiate with respect to y, well, this is not a function of y, so this is 0. And so you remember the derivative of 3y squared is 6y. You know, it's if we have, let's say we have y to the n, the derivative of y to the n is just n y to the n minus 1. Okay, but you know, maybe x and y are a function of some other variable like t, like maybe time or something. And we want to differentiate f with respect to time, okay? So we need to use the two-dimensional chain rule. That's just this here. So it's just the derivative of this function with respect to t is equal to df dx, then times dx dt, plus df dy, dy dt. Again, your two-dimensional chain rule. These actually should be not curly, they should be your standard d's. I'll change that. Okay, moving on. Again, this is just what we saw in the previous slide. Again, these should be your standard d's, not the curly d's. All right, so what I want to show you now is, let's say we take this and let's say instead of time, we're differentiating this with respect to x. I just want to show you that it reproduces our standard derivative with respect to x. So if this is respect to x, it's just df dx times dx dx, that's just 1. Df dy times dy dx, but y is not a function of x, so this is 0, so this is 0, this is 1, so df dx is just df dx. Right. Okay. So again, you can do that for this. Again, you get 7. Okay. This is, you know, this multi-dimensional chain rule, or well, two-dimensional chain rule in our case, is rather important in thermodynamics. So I changed my slide at the last second and just recopied it up here. So, you know, you've seen this guy in your thermodynamics class, but let's just kind of figure out where it comes from. So we have this this change in internal energy. So let's just remind ourselves of our two-dimensional chain rule that we just saw. Let's say we're looking at the internal energy with respect to temperature and volume, and we want a multi-dimensional chain rule. So that's du dt, dt with respect to something, du dv, ddv with respect to something. Your thermodynamics books often leave it blank or leave these as deltas. It's probably better to put these as delta and then divide by, I don't know, t, let the limit as t goes to 0 or something like that. But anyway, this expression here is basically this here, except it doesn't say, you know, what we're changing, what the other variable is. We've seen this du equals dq minus pdv, but you know, dq did what? You know, maybe it's time, who knows? It's usually time. It could be temperature, I don't know. Anyway, so this is not just, you know, from nowhere, it comes from your multi-dimensional chain rule. Anyway, okay, so we have this here, okay? And we have our change in internal energy here. So basically what I want to do is first I want to rewrite this in terms of our heat capacity. Just want to change just one thing. This du dt at constant volume, we know that's CV, okay? So this is the same here except we have CV, okay? So we take this bit here, we know it's du, and we set it equal to this bit here, okay? And then we just we move this to the other side and we solve for dq, okay? So we have this here, so we have dq is equal to these bits here. It's on the next slide also. Okay, so we have this from our previous slide, okay? So now let's choose some constant pressure path. What does that mean? Basically, maybe our system is expanding. Okay, so at each instance, we match the internal energy, the internal pressure of the system to the external pressure. Okay, so we have this constant pressure path. The pressure is infinitesimally the same at each instant. I think that's clear. Okay, we know what the change in heat with respect to constant pressure. Well, that's just Cp dt. Okay, we know heat capacity is dq dt. If we want it at a constant pressure path, Cp is just dq dt. Okay, so we replace this with this. Okay, so that's all we did here. So now we're going to divide by dt. Again, your calculus teacher will scream and yell at me. You can't actually do that. You divide by delta t. You let the limit as delta t goes to 0. Okay, so we're dividing by dt. Anyway, so we divide by delta t. We let the limit as delta t goes to 0. We get this expression here. Okay, great. This is getting close to what you have seen previously. Let's look at the next slide. Same thing here, but now if we subtract CV over here, we get CP minus CV is equal to a bunch of things here. Okay, but now let's reduce. This is for all gas, interacting gas, but let's just reduce it for an ideal gas. Remember, one of the tenets of an ideal gas is that the particles are not interacting. Okay, so if we fix the temperature and move the particles around, since they're not interacting, it doesn't matter how far they are apart from each other. Okay, so du dv at constant temperature is 0. This is rather important. Let's say this again. So again, let's say we just have a collection of particles. Okay, so at a constant temperature. So if these particles, and our internal energy is defined by this, by the temperature of this collection of non-interacting particles. If we move these particles away from each other, since they're not interacting, but we fix temperature, then the change in internal energy of the system is 0. Similarly, if we push these particles closer and closer together, again, since they're not interacting, the change in internal energy is still 0. And okay, that should make sense. Great. So since for an ideal gas, du dv at constant temperature is 0, this whole term here is 0. Okay, so we have Cp minus dv is just equal to P dv dt at constant pressure. But I said for an ideal gas. So here's our ideal gas law, PV equals nRT. So we can divide by P and solve for V. Then if we take this and differentiate with respect to temperature, well, the T just goes away. So we have dV dt is nR over P. Okay, so this expression here is just nR over P, but P and P cancel out. So we have Cp minus Cv is just nR. So this is the, this is your ideal Cp minus Cv equation you're familiar with for an ideal gas. Okay, we'll use this in a little bit. Degrees of freedom. So let's start with something here. Let's say I have some point mass just by itself, nothing else around it, free in space. So how many degrees of freedom does this point mass have? Well, it has 3 degrees of freedom. It can move in the x direction, it can move in a y direction, it can move in the z direction, okay? Let's say I have 2 point masses, just say point mass A, point mass B, and they're completely not interacting. But what is the total degrees of freedom of these 2 particles? Well, A can move x, y, z, B can move x, y, z. So 3 plus 3 is 6. Let's just do this argument one more time. Let's say I have 3 particles, A, B, C. What is the total number of degrees of freedom of these 3 particles? Well, A can move 3 ways, B can move 3 ways, C can move 3 ways. So the total number of degrees of freedom of these 3 particles is 9. Okay, keep that in the back of your mind. Okay, so argon. Argon is a monoatomic species. Let's assume it's a gas. So how many degrees of freedom does it have? Well, it can only move X, Y, Z, so 3 degrees of freedom. Nitrogen, again, let's just consider, before we think about what we know about N2, let's just think about one N atom over here and one N atom over here. The first N atom can move X, Y, Z. The second N atom can move X, Y, Z. So 3 plus 3, 6. So nitrogen, N2, has 6 degrees of freedom. But how can we, let's think about that again. So now let's think about N2. We know it has 6 degrees of freedom. The first nitrogen can move X, Y, Z. The second second nitrogen atom can move X, Y, Z. So 3 plus 3 is 6. But now let's put the center of mass, let's change to a center of mass system. Okay, let's put a center of mass, between these two nitrogens. So how many ways can the center of mass move? Well, 3, X, Y, Z. Okay, so the coupled system, N2, one N atom and another N atom, can move in 3 directions. In the X direction, in the Y direction, in the Z direction. This molecule can move 3 different directions, okay? But since we're talking about the coupled system, it can also rotate about this center of mass. It can rotate, like a clock, like if you're looking at a clock, the hands of a clock, it can move around the center like that. It can move the other way, perpendicular, okay? Like, I don't know, you move the clock is now on the ceiling for whatever. The hands of the clock moving like they're on the ceiling, okay? So it can move like that, like this. And if you try to rotate it about its axis, like you have a stick in your hand and you're trying to rotate the stick with your fingers, think about it rotating a chopstick with your fingers, not actually moving it, but that doesn't change there's no appreciable moment of inertia about that axis, so that one doesn't count. So that's 5, okay? But so nitrogen has 1 vibrational degree of freedom, okay? So that makes 6. 3 translational, 2 rotational, 1 vibrational, 3 plus 2 plus 1 is 6. So again, the degrees of freedom is conserved. We have 6 if we look at the 2 nitrogen atoms individually, and we have 6 if we look at the system itself. Okay, so carbon dioxide, there's 3 species, a carbon, an oxygen, and another oxygen. If we look at these individually, they can go 3, 3, 3, XYZ, 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 so that's 9 degrees of freedom. So now let's look at the system. If we put this in a center of mass system, the molecule itself can move in the X direction, in the Y direction, in the Z direction. So that's 3 translational degrees of freedom. It's linear, like nitrogen. So it has 2 rotational degrees of freedom. And carbon dioxide has 4 vibrational degrees of freedom. Okay, so I'm gonna talk about that a bit, but 3 plus 2 plus 4 is 9. Okay, so again, degrees of freedom of degrees of freedom are conserved no matter how you look at it. But let's take a quick look at at CO2 about these. So here's carbon dioxide, okay? So let's look at the degrees, let's look at the vibrational modes, okay? So there's the first one is this symmetric stretch. The oxygen atoms both at the same time go in and then both at the same time go out. So they move symmetric with respect to each other. There's the asymmetric stretch. I have these written down on another slide. So this frequency is maybe 1400 wave numbers. The asymmetric stretch may be 2300 wave numbers. Asymmetric stretch, one is going out, one is going in, and then they switch. This one goes in and this one goes out. Okay, so asymmetric stretch. Then there's 2 more vibrational modes. They're called bending modes. Okay, in this case, consider this picture here, and we're fixing the oxygen atoms, okay? And so this guy bends, let's say it goes up and it goes down, and it goes up, and it goes down. So that's one of the two degenerate bending modes. They each have a frequency of 667 wave numbers. The other one is this this carbon atom comes out of the page, then it goes into the page, and it goes out of the page, then it goes into the page. Okay, so that's the other bending mode, both at 667 wave numbers. They're degenerate. Okay, so keep that in mind. I don't need this anymore. Okay, so just a review of what we just talked about. One atom, one species, two species, three species. Degrees of freedom, 3, 6, 9. Translational degrees of freedom, 3, 3, 3. Okay, rotation, 0. Both nitrogen and carbon dioxide linear. They each have 2 rotational degrees of freedom. Vibrational degrees of freedom. We know nitrogen has 1 vibrational degree of freedom, and we just learned that carbon dioxide has 4 vibrational modes, vibrational degrees of freedom. 3 plus 0 plus 0 is 3. 3 plus 2 plus 1 is 6. 3 plus 2 plus 4 is 9. Okay. We're back here. Remember, now let's tie this all together. Previously, we took the derivative of our internal energy, I and our T over 2. Okay, we took the derivative with respect to temperature, and we got CV equals I and R over 2. Then we changed it to a dimensionless form by dividing by NR. So we have CV over NR is I over 2. Okay, so now let's consider argon. Argon has 3 degrees of freedom, all translational. So how do we get the heat capacity from this? Well, the first translational degrees of freedom has units of has internal energy, has heat capacity CV over NR of 1 over 2, so 1/2. Okay, the next one has CB over NR of 1 over 2. The next one has CB NR of 1 over 2. Okay, so that's 1/2 plus 1/2 plus 1/2 is 3/2. So the internal energy of argon, the heat capacity at constant volume of argon is CV over NR is 1/2 plus 1/2 plus 1/2 is 3/2. You have to add all the contributions of heat capacity together. That seems simple so far. Okay, so what about nitrogen? We know nitrogen has 6 degrees of freedom. Okay, so for translational, CV over NR is 1/2 plus 1/2 plus 1/2 is 3/2. Rotational, CV over NR is 1/2 plus 1/2 equals 2/2. Okay, now the vibrational frequency, the frequency of the vibrational mode of N2 is 2359 wave numbers. Okay, if you use Einstein's equation, I'll show you how to use that in a second. You'll find that the contribution for this mode is basically 0. Okay, you can also calculate the probability of this vibrational mode being populated. You'll also find it's about 0. So the heat capacity of nitrogen, CV over NR, is about 3/2 plus 2/2 plus 0. 3/2 plus 2/2 plus 0 is 5/2. You have to add all the contributions of the heat capacity together. Let's look the Einstein equation, then carbon dioxide. So this is the Einstein equation. You do this for each of the vibrational modes. Okay. Why are we doing this for vibrational mode? Maybe I didn't say that. So the equal partition of energy theorem is a classical argument. It assumes that remember I said earlier that it assumes all the modes are equally populated. Well, one, that's not true. Many of the vibrational modes at room temperature have a low degree, have a low probability of being populated. There's a there's a low probability to add energy to that mode, to excite it to another energy level. To add energy to a mode, we have to excite it to a higher energy level, okay? So whatever the ground state vibrational modes are, there's a low probability of us exciting those at room temperature. So if we want to, okay, so if we're looking at heat capacity, so heat capacity is the change, if we add energy to a system, how much does the temperature change, okay? So basically it's asking if we have these vibrational modes, okay? If we can add energy, if we can excite them, then the system can accept energy, okay? So that's basically heat capacity, okay? Great. Okay, so now how do we use this Einstein equation? We have to use this for every vibrational mode, okay? So a little difficult to calculate, but this is the only hard part of the lab you'll manage. Just keep in mind that this is your frequency. I give them all I give you each of these in the lecture. I'll show you CO2 in just a minute. Now be careful here with the speed of light. This is in centimeters per second. All these other things are SI units. This one here is centimeters per second. Okay, so be careful with that. Why is this one centimeters per second? Because this is in wave numbers. Wave numbers are inverse centimeters. Okay, so carbon dioxide. We know it has 9 degrees of freedom, 3 translational, 2 rotational, 4 vibrational. So we have to use Einstein equation for each of these vibrational modes and add them together. You add the contribution to the translational, you add the contribution to the rotational, and of course you add the vibrational modes together. There are 2 degenerate bending modes, 667 wave numbers. You plug it into Einstein equation once, you plug it into Einstein's equation again. You add both contributions for the degenerate bending modes. You will find that these have a finite contribution to the heat capacity. The symmetric stretch, about 1388 wave numbers, there's a very small contribution, but it's not nothing. And the asymmetric stretch, you'll find it has no contribution, like 0.0000. Okay, so again, remember, when you're adding these heat capacities together, you add all of them together. You use the classical arguments for the translational and rotational. Okay, so translational, CV over NR, because CV over NR is 3/2. Rotation, it depends how many rotations there are. Each of the translational modes contributes CV of NR of 1/2, but there's 3 of them. So that's 1/2 plus 1/2 plus 1/2 is 3/2. It's 1/2 for each of the rotations. The 2 linear species have 2 rotational modes. So that's 1/2 plus 1/2. And then you add to that the contribution due to the vibrational modes. So you'll get something for the first degenerate bending mode, you'll get something for the second degenerate bending mode, you get a very small amount for this, and you get basically nothing for this. You add all those together. Students make some strange mistake here in the past. Okay, so again, we're not doing the experiment this semester because we're not in the lab, but you can come back next year if you, it's kind of a fun experiment. It works. I spent a long time building this. It works perfectly well. Anyway, it gives you wonderful data. Everything of this experiment works out perfectly. Anyway, in the experiment, in the lab, we have these gases. They're in cylinders. You connect the tube to your first gas. Okay, your TA will help you. You add a small amount of, let's say, nitrogen to your resonance tube. So then you apply a given frequency. You apply a sound wave at a given frequency, let's say 1500 hertz. And you look at an oscilloscope, and on the oscilloscope, there's something called a Lissajous figure. It starts out kind of like a circle. And then you move a plunger through the resonance tube. There's a speaker and a receiver. You're changing the distance between the speaker and the receiver. And so you're looking at the change in the Lissajous figure as you move the plunger along the wavelength. Okay, so basically what you do is you get, well, depending on how you do it. So in the lab, we would get a half wavelength. We would get a half wavelength in centimeters. We would multiply that by 2, divide it by 100, and then multiply it by the frequency to get the speed in the speed of sound in that gas. Be careful. In the previous slide, we saw Einstein's equation. We saw a c here. This is not the speed of light. This c here is the speed of sound of your gas. This c here is the speed of sound in your gas. Okay. Okay. So let me go to the next slide, and then we'll come back. This is what you need to do. I gave you data. It's on Canvas. Yeah, so this is your data I gave you on Canvas. Okay, so what do you do with this data? You take this value here and you subtract it from this value here. Or excuse me, you subtract these two values. Okay, you multiply it by 2, you divide by 100, and you multiply it by this number. Okay, so that gives you a speed. You do the same thing for all of those. Okay, but you'll take the average value of you'll take the average value of these two, you take the average value of these two, you take the average value of these two. I worked out the numbers are the same, so it doesn't really matter. Then you put those in your table. But in the lab, you won't get the exact, in the experiment, which you can come back next year and do, it won't give you the exact same value. Okay, so that's how you get this column here. Now, CV of our experiment. Okay, so that's, you take this speed, you go to the previous slide, that's this slide, please stop, go away. You look at this here, okay, R, T in Kelvin. This C, again, is the speed you just calculated. M, be very careful here. All these are SI units. So you're used to seeing this as grams per mole. This is kilograms per mole, okay? So convert your weight from grams to mole to kilograms per mole. Okay, so that'll give you this column here. And the theoretical value, okay, that's using your equal partition of energy theorem plus your Einstein's equation. Again, it's translational plus rotational plus vibrational from Einstein. Translational plus vibrational, translational plus rotational plus vibrational. Translational plus rotational plus vibrational, okay? Argon, for example, is just 1/2 plus 1/2 plus 1/2. So 3/2 for translational plus 0 for rotational plus 0 for rotational. So you all should get 3/2 for argon. N2 is just 3/2 for the translational, 2/2 for the rotational, and about 0 for the vibrational. So 3/2 plus 2/2 is 5/2. For CO2, it's 3/2 plus 2/2 plus the contribution from the first 667 wave number bending mode, plus the contribution from the second 667 wave number, plus the contribution from the 1388 wave number vibrational mode, plus the contribution from the 2359 wave number fourth vibrational mode. So you have to add all those together and you get some number, okay? So this column here, the value here from this, these two columns should match extremely well, very well. Okay, if these don't match, you did something wrong. Okay. So again, we're not in the lab, but maybe you'll come back next year and do the experiment. Basically, we keep the flow rate of the gas low. Let your TA, if you're not familiar with using large gas cylinders, let your TA help you. If you have put too much pressure in the resonance tube, it can shatter. So again, you always have to have goggles on in this lab and in every lab. You know, I wear gloves in this lab and all labs, unless it's specifically said you don't have to wear gloves. You know, labs can have contaminants from other experiments, okay? And that's about it. All right, thank you.